Can you hear? Does it sound okay? Okay. Yeah, so thanks for the opportunity to speak, and thanks for putting together this wonderful workshop. So I met Fred Cohen only once when I was a grad student around 2012. He gave some talks at UChicago about grade groups and configuration spaces. The talks were great. I remember talking to him in the tea room with a group of other graduate students, and as many have mentioned, he was extremely generous with his time and enthusiastic about math, which I appreciated. After talking to him, I went home to try to look up some of his papers and some of the specific results that he had mentioned. And I was a little bit surprised by what I found. So to show you what I mean, here's a few of the titles that I came across. And as a young graduate student who was somewhat desperately trying to find good things to read, it was a little distressing to come across so many papers that seemed to all have the same title. But even so, I was struck by Fred's ability to return to the same foundational topic again and again and say something new. Okay, so yeah, so this talk is about Nielsen realization, and it's joint work. So previous joint work with Lei Chen and current and ongoing joint work with Corey Bregman. So I'll start sort of general, tell you about the Nielsen realization problem. So let's say M is a closed oriented manifold. So Nielsen realization is something about group action. So we'll have the group of homeomorphisms of M. And the mapping class group, which is homeomorphisms up to isotopy. The group of path components. And there's an obvious surjective map. And the question is, if we have G, which will be a finite group, which is a subgroup of the mapping class group, can we, or when can we find a lift like this? So for example, in the case when G is the cyclic group of order 2, we can rephrase this problem as follows, just to give you a sense of what this is asking. So if we have, if F is a homeomorphism of M, and F squared is isotopic to the identity, does there exist a G, which is isotopic to F, such that G squared is equal to the identity? Okay, so the F square isotopic to the identity is a Z mod 2 subgroup of the mapping class group, and then the existence of G is exactly asking if you have this lift. Okay, and let me give you, so I want to give two very concrete examples, which we'll return to sort of later in the talk. Two instances of this problem for 3 manifolds, which would be the central focus later. Okay, so the first example, right. So I need to give you an M and an F. And F squared will be isotopic to identity. So in the first example, M is going to be S2 times S1. And to construct F, let me start with S2 times the interval and build the map there. So the map is going to be, so I'll write this as send the pair v comma t, v is in the sphere, t is in the interval, to, well, so I'll rotate. So, okay, let me just write it briefly. Okay, so this is a formula for a diffeomorphism of this. Maybe this should be 2 pi. I wrote this. And it's the identity at when t is 0 and 1. So it descends to a diffeomorphism of S2 times S1. And that's F. And F squared is isotopic to the identity. The reason for that, watch closely, is that. Okay, so that's the first example. So the second example will have a similar flavor. I'll start with the torus now, times interval. And the map is going to be v comma t goes to this pair. Okay, so I'm thinking of the torus as r squared mod z squared. So there's an action of SL2Z by affine automorphisms, and you can translate. Okay, so this is well, this is a map. It descends to a certain closed 3 manifold, which, so M here is going to be quotient. Says that it's going to be a mapping torus where I identify v comma 1 with so the monodromy is going to be this matrix 1, 2, 0, it's just this matrix. Okay, so this is a certain mapping torus. Okay, so M, it looks like this. So we have, okay, and then so this you can check, it's not hard that it descends, and then F squared, well, you just write the formula for it, and you find that it's given by applying the monodromy in the first coordinate, and it's constant in the second. So you see that this is isotopic to the identity because, well, you can get an isotopy from the identity just by sort of pushing all the fibers one period, which has the effect of doing the monodromy. Okay, so so this is 2 concrete instances of this problem. In each case, we want to know is this F isotopic to an involution? And for one of these, the answer is yes, and for the other, the answer is no. And we'll see which is which a bit later. Okay. So now let me zoom back out a bit and give you a little bit of motivation. For the Nielsen realization problem. So one is, well, it's sort of just a basic question about symmetry. But to put a finer point on it, if M is aspherical, so it's a k pi 1 space, and N is 2 or 3, so it's 2 or 3 dimensional, then the mapping class group is isomorphic to outer automorphisms of the fundamental group. And so you can think of this problem as you have some finite group of symmetries of the fundamental group, and you want to know when can you promote that to a finite group of symmetries of the manifold. And stated like this fits into what sometimes called Borel's theme, which asks to what extent are topological properties of an aspherical manifold determined solely by the fundamental group. Okay, so in the context of Nielsen realization, what you might hope is that just using information about pi1 of m, you identify some obstructions which tell you everything. And in the absence of finding any obstruction, then you sort of expect that you can always realize things. Okay. A second motivation is a connection to geometry, maybe geometrization. So Nielsen's original question was slightly different than how I phrased it. So let me tell you what that was. And there's a more general version asked by Shane and Yao, which asks if, well, right. So if you have G a finite subgroup of out of pi1 of m, and m has a Riemannian metric with negative curvature, negative or non-positive, let's say negative, does there exist an isometric action G on M, I guess an isometric realization, so action inducing the given one on pi1 with respect, so isometric with respect to some negatively curved metric. Okay, so this is a finer version. Well, knowing this for yeah, so metric realization, just in the surface case, which was what Nielsen was originally interested in for just a surface of genus G. This will give you that if you have a three manifold, so this is the relation to geometrization. If you have a three manifold, which is fibers over the circle with fiber closed surface, and with finite monodromy, if you have this metric realization, then so the monodromy is just valued in the mapping class group. If you can realize it as isometries of, say, a hyperbolic metric, then this tells you this has metric, which is locally modeled on H2 times R, which is one of the Thurston geometries. So this is a small sort of piece of geometrization. Okay. So let me give you one more, which is about flat connections. And well, I'll be a little brief here. So so given a M bundle, well, okay, I'm going to think that these are manifolds for now, and this is a smooth thing. So you can put a connection which is like a horizontal distribution on E, and then flatness is about whether that's integrable. So for a bundle, you can ask whether it has a flat connection. And a flat connection is some sort of foliation of horizontal. It's like a horizontal foliation on the total space. And if you have this, what you get at the group level is that the monodromy of the bundle, which is a homomorphism valued in the mapping class group of the fiber, this lifts to homeomorphisms or diffeomorphisms of the manifold. Okay, so so if you have a flat connection, then there's some solution to the realization problem for the monodromy. In general, it's hard to show that bundles don't have flat connections, but Nielsen realization is an approach to doing that. Okay. Okay, so now let me tell you a few things that we know. Feel free to stop me if you have questions at any point. Okay, so I'll tell you some results and then we'll move on to three manifolds. So this just give you some sense of the lay of the land. Okay, so in terms of geometric realizations, in the sense of Nielsen and Shen-Yao, so these exist for M hyperbolic. So this is by work of Kirchhoff in dimension 2, which we heard some about yesterday. And in dimensions 3 or greater, this follows from as a corollary of Mostow rigidity. So in general, you can't expect geometric realizations, so that they don't exist generally for negatively curved manifolds. This was first observed by Farrell and Jones using exotic smooth structures on hyperbolic manifolds. And maybe one other thing I'll say is that, well, I think it'd be interesting to think about what happens in dimension 3. I'm not going to say anything about that. But from talking to Shmuel earlier this week, I realized it's not completely obvious. Oh, well, if you do non-positive curvature, whether, yeah. Mm-hmm, mm-hmm.
Sorry,
Yes.
Could you just state exactly what that bottom blackboard says in more details? What is the theorem there?
Yeah, so yes, sure. So this part is essentially a positive answer to the Nielsen-Shen-Yao question. But specifically, it says if M is hyperbolic and you have a finite subgroup of outer automorphisms in the fundamental group, then there exists a hyperbolic metric for where you could realize that finite group by isometries. In dimension 3 and greater, that metric is unique. Yeah, Mostow tells you that the outer automorphisms of pi1 is isomorphic to the isometry group, and so then you clearly have a realization of the whole group. Yeah, but in dimension 2, that's Kirchhoff. Is that okay? Yeah. And what Farrell and Jones actually do is they find examples where diff M to out of pi1 of M. So these are negatively curved manifolds where this is not surjective. And where this is a finite group. And so you can't realize the whole thing. So it's a negative result. Okay. Maybe I'll also mention that there's some recent work for four manifolds which are simply connected due to Farb and Luyenha, which, well, yeah, I guess it's even less clear what I mean by the geometric realizations, but they're looking at things like K3 surfaces, which have certain interesting metrics or complex structures, and studying sort of from the Teichmuller theoretic point of view, these sorts of realization questions. Okay. Okay. Let me say a couple more things. Okay, so if you drop the geometric criterion, then, well, here's something that we don't know. So if M is negatively curved, does homeo to out of pi1 is a split. When, well, generally we don't know it when n is at least 4. Okay. And out of pi1 is a finite group with that assumption. Okay, and then the last sort of thing I want to say about results is that there are obstructions to realizing, say, a finite subgroup of out of pi1 that live in the third cohomology of the group with coefficients in the center of the fundamental group. So these, I believe, go back to work of Raymond and Scott, who showed these obstructions are generally non-trivial. And well, it turns out that this is a complete obstruction for irreducible three manifolds. Okay, so I'm not going to tell you how the obstruction is defined, but well, there is some group, yeah, I mean, right. So this follows from many works, most notably there are works of Zimmerman, but also several others. And you can think of this as some sort of triumph of the Borel theme, right? I mean, this is just a purely group theoretic thing, which tells you whether or not you can realize or not. Okay, so for example, this well, so example 2 above, F is not isotopic to an involution. And you could see that the obstruction is exactly here. Okay, so like this three manifold is a cipher fiber space, and it has some non-trivial center, which contributes to the obstruction. Okay. So now I want to turn to three manifolds and tell you more specifically the story there. But are there any questions before I do that? Okay, so the three manifold case, it's sort of the first, it was the first dimension where the answers, there's some positive and some negative answers, so there are non-trivial obstructions. And I think it's sort of in a sweet spot in terms of, it's, well, as it turns out, it's somewhat complicated, but thanks to things like geometrization, we know a lot and can understand a lot. Okay. So for the rest of the talk, M will be a closed oriented three manifold. Okay. And right, so well, as you already see, there's sort of different versions of Nielsen realization. You can have mod, you can have out, and generally these are different. So let me state sort of the general problem that we want to understand. So I'll write it like this. So there's a sequence of maps. We have out and mod, and this is diff with the discrete topology. So this is just k pi 1 for the diffeomorphism group. And then we have, so G finite group, always. And well, we have BG, which will map somewhere on the right. And then you want to ask the lifting somewhere to the left of that. Okay. And so there's several versions of this lifting problem, and each of them, tells you something interesting. I mean, like the difference between these two is like bundles versus bundles with flat connection. Here, this is like if you have, when is a finite group the monodromy of some bundle, and so on. Okay, and we'd like to be able to solve each of these. And I'd like to propose sort of a general route to doing that. Okay, so right. So let me just get on to that. So the general strategy. So this is tropicalized. I didn't think about that. That's, we'll do something different. Okay, so this is a general strategy to construct lifts, and to identify obstructions. Okay, and before I give you this sort of the steps, recall that a three manifold has a prime decomposition. So M we can write in the following form, where these Ni are irreducible, which means that any two sphere in N embedded two sphere bounds a three mole. Okay, so right. So the thing about this is, so the factors in the prime decomposition are unique. But the spheres in the connect sum, the spheres, there's spheres here which are not unique up to isotopy. And it's that non-uniqueness that's well, causes a lot of problems. And right, so the result, which maybe I erased. Oh, no. So we sort of already know what's happening for irreducible three manifolds, or we know, not sort of, we know. And so really it's about understanding what's going on for the reducible case. And maybe I'll also say that, so geometrization tells you that each of these NIs has a decomposition where you cut along tori and then you get geometric pieces. So you should think that maybe these NIs are like hyperbolic manifolds or Seifert fibered or something like that. Generally, it's a little more complicated. Okay. Okay, so, right, so the strategy now. Okay, so the first step is to use something which I'll call sphere decomposition theorems, and I'll say what that means in a second. Say what these are. To reduce to the reducible case, or the irreducible case. So then there will be some problems to solve for irreducible manifolds. And the problems, as you'll see in a second, aren't, I mean, you can't just exactly plug in this here. So you'll solve the problems or identify obstructions in general, and then you glue solutions or identify obstructions to gluing solutions. Okay, so, well, if you remember back to Monday, this might look familiar from like Rachel's talk. This is basically the same 3 steps, something about spheres and then pieces and yeah. But it'll be a little different. So the first step is where the difference, well, it's already different at the first step. So okay, so okay, let me tell you something about these sphere decomposition theorems. So this is sort of, yeah, so there will be several, these are sort of the main structural results that elucidate what's going on. So so G will continue to be a finite group. So the first one is a theorem of Meeks and Yao, which tells you about the structure of finite subgroups of diffeomorphisms of M is closed oriented 3 manifold. So for every such finite subgroup, there exists a collection of embedded 2 spheres, which is G invariant and such that if you cut M along this collection, which let me call the collection S, script S. So this is, so, well, okay, so what this notation is meant to mean is you have your 3 manifolds, you have some collection of spheres. You cut along them, and then you get 3 manifold with some boundary components, which are S2s, and then you fill those in with B3s. And that's sort of what this MS is. And this is it has irreducible components. Or it is irreducible. Okay. Okay, so any finite group action on a 3-manifold has this collection of spheres that you can cut along, and then it's built from actions on irreducible pieces in this way. Okay, this is extremely useful. Corey and I figured out a version for the mapping class group. So if you have G, which is in mod rather than diff, well, what you'd like and what you can show is that there exists, again, some collection of embedded 2 spheres, which are G invariant up to isotopy. That's the only thing that makes sense. I mean, G is only in mod. And this spherical closure is irreducible. There's a version of this for subgroups of out. It's a Hensel and Keelock. Which, let me just state it briefly. So for every G in out of pi 1, there exists well, a graph of groups gamma for the fundamental group. Let me not spell out exactly what this means, which is G invariant. So, well, what it is sort of in example, these are similar type of things that, well, right, in Karen's talk, she explained what outer space is, which is space of graphs. So that's sort of the case when pi 1 of m is a free group. But more generally, Girardel and Levitt, for groups that are, pi 1 of m is a free product of groups, you have, well, yeah, so how these things look is like these, it's a graph, the vertices are labeled by the fundamental groups of the irreducible pieces. And the fundamental group of this graph of groups is gamma. And G is acting. So G acts, think of G as like some symmetries of this graph. Okay, so the high level upshot is that for diff, mod, or out, you have some structure for finite subgroups, and in terms of how, well, okay. Okay. Right. So let me say 2 things quickly about this. Oh, yeah, so a few remarks. Yeah, so that Hensel-Keelock theorem is proved again with this. You can formulate it in terms of a Teichmuller theoretic kind of statement, where there's some Teichmuller space of these graphs, and they show there's some fixed point. And we bootstrap their theorem to prove ours. The Meeks and Yao thing is something completely different. It's proved using minimal surface techniques. Maybe I also mentioned that, yeah, so one important remark is that the S is not typically unique. And that causes some problems for this strategy. Well, okay. And then maybe one other thing is that I don't know a version of this sphere decomposition theorem for BDiff, but it would be interesting to know. I mean, it's sort of, well, it's clear what statement you would want. Now, if you have a map from BG to BDiff, where G is a finite group, you want to be able to split your bundle along subbundles, which are two-sphere bundles, and so that the pieces would be irreducible bundles. But I don't know whether or not you can do that always. Okay. Okay, so are there any questions? Okay, so let me try to show you this strategy in action, and I'll demonstrate it just in the simplest lifting problem for mod to out. Okay, so the first thing is, well, so there's an exact sequence. So the kernel of this map is understood, and it's what's called the twist group of M. So this is generated by twists, sort of this form, about two spheres embedded in M. So there's an exact sequence like this. And we're interested in this lifting problem. And well, the obvious obstructions, which I'll call them algebraic obstructions, are that, well, first of all, G, this map is not generally surjective, it's map alpha. So first of all, G had better be in the image of alpha if you want to lift. And then there's an Euler class, from the theory of group extensions in H2 of G with coefficients in the twist group. Okay, so well, you might sort of consider this to be an answer. This is a complete obstruction to splitting. But I'd like to argue that, well, this maybe you think of as an algebraic translation of the problem, and you haven't quite solved it. I mean, unless you really understand these extensions. Okay, and so let me give a different perspective on it. So using the sphere decompositions. So the geometric obstruction. Oh, yeah. Let me put a finer point on it. So first, as an example, when M is a connect sum of S2 times S1s, then this map from mod to out of pi 1, this splits by work of Brendel, Broadus, and Putman. Well, this is kind of surprising. This is out Fn, out F G, and the whole group splits. So in particular, any finite subgroup splits. Okay, and well, that's maybe not apparently obvious. Just when you, I don't know, write down, you have the Euler class. So the geometric point of view on the obstruction is, well, that there exists an isotopy class of sphere system. No, sorry. There exists this gamma graph of groups for G, which is G invariant, that is induced by a sphere system, isotopy class of sphere system in M. Right. So if you, so yeah, I mean, maybe I should have said at this point, you can always go down. I mean, if you have G acting on M, you get the sphere system, then the isotopy class, and then you get the graph by taking the dual graph. And the obstructions come by thinking about how to go back up. And so going from out to mod, you have this G graph of groups, which necessarily, some G graph of groups necessarily must be promotable to a sphere system. Okay, I'm short on time, so right, so let me just say, okay, so let me just say something brief. So from this point of view, you get various obstructions. If you just think about what is the difficulty of starting from this data and going to the spheres. And one type of obstruction you get looks like, so for n irreducible, you want to know, you have the mapping class group of n relative to k disks, mapping to the mapping class group of n relative to k points. And the kernel of this is generated by like the boundary twists. Twists about the boundary of these. And you want to be able to split this over finite groups. This is one type of obstruction that you encounter. And well, for example, I mean, in this case, this is really the main sort of obstruction where n is the 3-sphere. And then you can use this Mail conjecture proved by Hatcher to identify what these groups are and what the extensions are. So for n is S3, then how this sequence looks is, so this is like Z mod 2 to the k minus 1. And this group here is the symmetric group from k, and it's not so hard to see that this splits. So sort of the local obstruction for this irreducible piece vanishes, and you can use that to see, to give, I guess, a new proof of Rendell-Broadus-Putman, the splitting over finite subgroups. But then for other geometries, like for hyperbolic things, there's a non-trivial obstruction. And so, well, okay, so you can study these things. Right. So let me finish with a problem. Yeah, so hopefully this gives you some idea of the program, and you see a little bit of how it works. I mean, it's still very much work in progress to figure out the final answers for all of this. So it's maybe lucky that I'm out of time, almost out of time. So I don't have like a general theorem quite to state. Right, so let me just finish with one question, which is related to, well, connects to configuration spaces. So this is related to the BDiff M to mod M splitting problem. This is one of the obstructions that you sort of meet when you try to solve that lifting problem. So n is, yeah, so just to be concrete, let's say n is a hyperbolic manifold. Then you have, so I'll look at the pure configuration space of k points on n. Oh, and G is a finite subgroup of isometries. And well, so on the one hand, there's fixed points of this, but then you also have homotopy fixed points. And there's an inclusion. And the problem or question is, well, what can you say about the quality of this map in this very particular special case? And if it helps, think of a three-man, well, hyperbolic three-man. So like, is this, well, one thing that would be nice to know is this a pi not surjection? But you know, for all I know, maybe it's a pi not iso, or maybe this is a homotopy equivalence. Right. Okay, maybe that's all I'll say about that. Yeah, and so, right. Well, I'm out of time, so maybe I'll just stop there. Thanks.
Any questions for the speaker?
That mod